Hello everyone, and welcome to this walkthrough on estimating cloud deployment energy profile using Google Cloud Platform. In this video, we'll explore how cloud workloads consume energy and why sustainability is an important factor in deployment decisions. Data centers consume large amounts of energy, and depending on where that energy comes from, it can contribute to greenhouse gas emissions. That's where sustainability in cloud computing comes in. The goal is to optimize our deployment so they use resources efficiently and also minimize their carbon footprint. Here's the roadmap for today's session. We'll begin with a quick introduction to why sustainability in cloud matters. Then we'll move on to compute engine basics and understand how virtual machines consume resources, followed by a look at the carbon footprint tool. Then we'll move into monitoring resource usage, examining CPU, memory, disk, and network activity, and linking utilization to energy profile. Finally, I'll share some best practices for sustainable deployment and wrap up with key conclusions. By the end, you will know how to evaluate workloads and interpret their energy impact in Google Cloud. In today's digital economy, cloud services are everywhere, but the energy powering them often goes unnoticed. Data centers demand about 1 to 2% of global electricity, and depending on the region, that energy might be renewable or rely heavily on fossil fuels. Cloud offers a chance to optimize energy usage at scale. By choosing efficient configurations and low carbon regions, we can help in reducing greenhouse gas emissions, avoid waste, and lower the cost. In short, sustainability in the cloud is not just about saving cost, it's about aligning technology with environmental responsibility. Let's move into the Google Cloud Console and take a look at Compute Engine. Here, we can deploy virtual machines with specific configurations of CPU, memory, and disk. Here, the first graph shows CPU utilization over time. The line chart moves up and down, reflecting how intensively the processor is being used. Right below, you will notice the memory utilization graph. Next, we have the disk utilization chart. It displays read and write activity over time. Whenever the graph shows high activity, it means the disks are spinning more, consuming more power. In contrast, flat or lower lines mean the disk is mostly idle. Monitoring this helps us understand storage-related energy consumption. Here, we have the VM instance overview. On the left, you can see total number of VMs, their machine types, attached disks, and other key configuration. These settings directly affect both performance and sustainability. On the right, we have a CPU utilization chart for the top 5 virtual machines. The y-axis shows CPU usage percentage, which can go beyond 100% because vCPU utilization is counted across multiple machines. The x-axis represents time here shown in UTC plus 530. This snapshot captures activity between roughly 4:30 and 4:41 p.m. on September 6, 2025. Notice the spikes in the graph. Around 4:30 p.m., CPU usage shoots above 150%, indicating a heavy workload, likely batch processing, analytics, or multiple parallel processes. It then briefly drops close to zero, showing that the load paused or process is finished. Shortly afterward, it climbs again towards 100%, meaning new tasks started running on the VM. These peaks and dips help us interpret resource usage pattern and understand the energy profile of our workloads. Spikes mean higher power draw, while drops show idle or low energy periods. Switching to monitoring dashboard, we now see real-time graphs of CPU, memory, disk, and network activity. Here we have two charts. The left graph shows CPU utilization for the top 5 most active virtual machines, while the right graph shows the least active ones. Our virtual machine instance 202.5090611000 is included in both views. First, first we apply a filter for machine type E2 medium to focus on similar instances. Next, we add a filter for zone. For us, it will be US East to D. Notice how the graphs adjust to show only virtual machines in that zone, reflecting localized workload patterns. Then we further add a filter for region US East 1, which aggregates activity across all zones. Some spikes become less pronounced while others persist, showing differences in resource usage across zones. The vertical axis represents CPU utilization percentage, which can exceed 100% because multiple vCPUs are counted together. The horizontal axis shows time, here from around 4:30 to 4:41 p.m. Notice the spike above 150%, indicating a period of heavy load, it then drops close to zero, showing the workload paused or completed, and rises again towards 100% as new tasks start. Processes by CPU usage shows which processes consume the most CPU. Peaks here indicate resource-intensive tasks that could be optimized or distributed. System load per vCPU reflects overall demand on each virtual CPU. High values suggest that VMs are nearing full capacity. vCPU core usage. It highlights which cores are most active. Uneven usage may indicate imbalanced workloads. Unused vCPU cores shows cores that are idle or underutilized. High values suggest potential for right-sizing or consolidating workloads to improve efficiency. By analyzing these graphs together, CPU utilization, processes by CPU, system load, core usage, and unused code, we get a complete picture of VM performance and energy consumption. This visual analysis helps guide sustainable deployment decisions, ensuring resources are used efficiently and energy consumption is minimized. Next, we move on to memory utilization graphs. The left graph shows memory usage for the top 5 most active virtual machines, while the right shows the bottom 5. Peaks here indicate virtual machines running memory-intensive workloads such as data processing or in-memory caching, while lower values represent lighter usage. Monitoring these patterns help us understand which virtual machines are consistently using large amounts of memory and which have room for optimization. Below that, memory byte used and the memory bytes unused graph on the right highlights idle or free memory. High unused memory indicates opportunity for right-sizing virtual machines or consolidating workloads to reduce wasted resources. Next, processors by memory utilization on the left identifies which processors are consuming the most memory, helping pinpoint resource-heavy applications. On the right, memory by state shows a clear breakdown of memory that is free versus memory that is actively used. This helps us see whether memory is efficiently allocated and whether there is potential to improve utilization and energy efficiency. Next, let's look at the network utilization. On the left, the network traffic graph shows overall inbound and outbound traffic for the virtual machines. Peaks indicate periods of high data transfer, while valleys show lower activity, helping us understand bandwidth usage patterns. Next, we have several detailed breakdowns for the top virtual machines. Send traffic by destination shows where data is being sent, internal, external, or cross region. Sent external or different project. Highlights data sent outside the cloud environment, which can have higher latency and energy cost. Sent cross-region indicates traffic moving between different regions, reflecting global workloads. Firewall package denied displays block traffic, giving insight into security rules and potential wasted attempts. Next up are the disk-related graphs. The disk utilization chart shows how actively the disks are being used. High values indicate frequent read-write operations, while flat lines suggest idle disks. Disk throughput measures the rate of data transfer to and from the disk. Spikes here show periods of intense input-output activities such as database queries or large file transfers. Disk IOPS Disk IOPS track the number of input or output operations per second. High IOPS, like transactional databases, are more energy intensive. Input-output size reflects the average size of read or write operations. Small input-output size often indicate many quick operations, while large sizes point to bulk transfers. Input-output latency shows how long it takes to complete disk operations. Higher latency can signal bottlenecks or performance issues that may also impact energy efficiency. After storage, we also check supporting metrics. Logs provide a record of events and operations. Analyzing them helps correlate spikes in CPU, memory, or disk usage with specific workloads or processes. GPU utilization appears if GPU-enabled instances are in use. These graphs show how heavily graphics processors are being used, which is critical since GPUs consume significantly more power under load. Next, we move into the processes section, which ties resource consumption directly to the applications running inside a virtual machines. Processes by CPU usage. Processes by CPU usage and CPU per virtual machine reveal which workloads are driving computation, whether system-wide or isolated to a single machine. On the memory side, top 5 memory-heavy processors and memory per virtual machine show where applications are consuming most RAM, highlighting potential inefficiencies. For storage, disk throughput by process and virtual machine charts identify the most input-output intensive workloads, often linked to data-heavy tasks like backups or databases. These insights let us trace every spike in CPU, memory, or disk directly back to the process responsible, enabling better performance, tuning, cost control, and energy efficiency. With this, we have walked through all major monitoring graphs in the GCP console. To wrap up, sustainability in the cloud means right-sizing virtual machines, shutting down idle ones, and choosing low-carbon regions. Every virtual machine, every workload, and every region choice impacts energy use. In the end, sustainability isn't just about running the cloud, it's about running it smarter. Every choice we make shapes both performance and the planet. Let's choose wisely. Thank you for watching this walkthrough on estimating the cloud deployment energy profile with Google's Cloud Platform. I hope this session has shown you how to evaluate workloads, monitor their energy impact, and take steps toward greener cloud computing. Thank you so much.